Welcome back, folks. We're still looking at our kind of first BJT circuit as simple as we can possibly make it with just a couple resistors. Last few videos, we looked at how to check our assumption that the transistor was operating in the active region. Okay, but it's certainly not the only region that we want to operate in. If we start building logic gates out of these devices, and we can do that, we will do that. Then we want to push it to saturation so that it's a short, and we want to push it to cutoff so that it's an open, right? So we can represent a 0 and a 1. So we can take this same circuit, and that's what we're going to do. We're going to start with the same circuit. Let's take a look at that. And I left the analysis here, and I left the analysis there because all I want to do is change a value. I want to change a value of a resistor, and I want to push it to saturation. Okay, and there's a couple ways we can do this. We want this to look like a short, and if this looks like a short, then we're going to have 0 volts here. Okay, so if we have 0 volts here, we need to drop all of this 5 volts across RC. And there's a couple ways we can do that. The first way, I usually ask the class and I let you scratch your heads and try to figure it out for yourself, but you're not here, and oh boy do I miss y'all. Okay, so I want to drop all of the 5 volts from here across this 150 ohm. So I can do that by either increasing the current, right? So I times R is going to be bigger. I can increase the current through here to make this drop bigger. Or, well, let's leave that or. I want to increase that current. Okay, so I can't change beta. I'm not changing the transistor out. So one answer I sometimes get is, well, just raise beta. It's like, oh yeah, that's true, but I'd have to swap out the transistor. I want to make this transistor operate in saturation. So if I want to increase this current, well, this current through the collector is dependent on this current through the base. So one thing I can do is increase the current through the base, and that gets multiplied by beta, and that gets increased there. So I can increase that current by lowering this resistance, right? I can say instead of 86K, we'll go with yellow since it's a change. Let's make it 1K. Okay, as simple as that. Push a little more current in here, more current's going to flow here. We're going to drop more voltage across here, and we're going to see that change in the node voltages. So we got to find those node voltages. And I haven't really changed the circuit the way it's connected, so these equations are close. Okay, I didn't change the 150. What I changed was over here. I changed this to 1K. Okay, that's 1K. Now let's think about what's that doing. What that is doing. First video in the morning. Wake it up. I made the denominator smaller, which is going to make this whole term bigger, right? And this term is negative. So we're going to have to balance things out because of that, but this current becomes much bigger, so VC is going to have to change to balance that out, so these still equal to 0. But that's really the only change. So I copied the script in MATLAB so you don't need to watch me type it all again, because I know how thrilling watching me type MATLAB scripts is. So this is the same code. Here's the original one. Hey, look, it's still highlighted from copying, and it's the same one, but I made it a new file name just so I can post it for you. The only thing that's changing is this resistance right here, the denominator of that second term. And then we just run it. Okay. Whoop. Haven't run it yet. Doing it live. And what do we get for the solution? Solution that should still be 5, and it is. And that should still be 0.7, and it is. Here's the interesting one. And for VC, we get negative 124, which feels absurdly off, and it should. Okay. Oops. It's not possible. Okay. And this is negative 124. Okay, and if that feels funny to you, then good, it should, because all this can do is go from an open to a short, right? So it can only connect it down to ground, or it can connect it up to the 5 volts, and that's it. So it's got to live between 0 and 5 volts, and this very clearly does not. Okay, so something's up, and the question is what's up? And we should check these assumptions, right? We should check these assumptions, and we can do it in both ways. I want to get that table. I want to get that table that had the different junctions. Hold on one second. I'm not going to make you watch me fumble through files. Okay, so I stole this from previous notes, and it's behind my head now. Okay, and we want to look at this table again. We're not sure we're in the active region. We don't know what region we're in. We were hoping for saturation. Okay, so let's figure out how to use this table, and let's see if it works in this case. Okay. I could have done this off camera too. Okay, so we want to evaluate what's going on here. So we say, what's the voltage between B and E? So we have VB minus VE, which VE is still grounded, so this ends up being 0.7 volts, and we say that that is forward. Okay, so we know we're not in cutoff. Okay, and then we can say what's the voltage between B and C, and we have 0.7 minus negative 124. Okay, and that of course equals 124.7 volts. That's a very positive voltage. I think we'd probably have broken the thing by now, but it's not possible. Okay, but we can say that that looks like it's in the forward region, and if they are both forward, we can say correctly that this transistor is in the saturation region. Okay, so it looks like we saturated it. The other way we can look at this is we can say what's VCE, right? That's the other way that we can check our check the region of operation. So we can say VCE is equal to VC minus VE, which is equal to negative 124 minus 0, also known as negative 124 volts. Okay, and we look at that and we say, hey, VCE is less than 0, therefore we can say saturation. Okay, there we go. Just like that. All right. That's our circuit. So we know this analysis is no good because we assumed active and then we showed that it's in saturation. So we'd have to then go back and reanalyze it and say, hey, this is actually a short. Okay, let's do that. Let's grab this down here, and these are going to get boring real quick. Okay, we say, hey, this is a short, so we can take this out just about. Okay, let's leave that there because it's the diode piece of it. Okay, but this is shorted down here, and therefore we can say that VA, yeah, that's 5 volts. VB is 0.7 volts, and VC, we'll say it's equal to 0. It's going to be like really close to 0, but not actually 0, but close enough that we're going to assume it's 0. Okay, so we would have to reanalyze it, making the saturation assumption. That's it. We pushed it into saturation by lowering the resistance of RB. Next video, I'm going to show you a different way to push this transistor into saturation, and we'll check it, and we'll see that similarly we end up in saturation. Okay? Stay tuned and good luck, folks.